Hello, I'm Alex Halliday, Director of Columbia University's Earth Institute. We focus on the state of planet Earth and how we can build a more sustainable future for its inhabitants. As some of you know, Columbia now is building a climate school, which is being led by faculty from across the university. It's a very exciting time for us and keen to engage with you on this. I'm pleased to welcome you to the first of our Earth Institute lecture series called Earth Lectures for this academic year, as our world continues to grapple with the so-called new normal of life during a pandemic. We are, of course, doing this virtually. While we miss seeing everybody in person, and we used to sort of have regular gatherings downtown in Manhattan, we can connect with so many more people this way, and we're expecting over 1,000 people tonight, and it's going to be a very exciting, people are very, very interested in this particular event tonight. So it's been great to be able to open it up to so many more people around the world. So welcome one and all. Today's lecture is quite extraordinary, as we are discussing what is actually a present emergency happening right now in this country. Our subject is the unprecedented wildfires now burning up the western United States. This year, California has seen 6 of the 30 largest fires on record. In mid-August, a highly unusual barrage of dry lightning sparked infernos that are still burning. In Oregon, some areas have not seen such intense fire in 300 to 400 years. Across the West, high temperatures and drought, of course, helped fuel the flames, and we'll be hearing a bit about that today. And actually, the sobering thing, and perhaps the most devastating thing of all, is that as of today's lecture, there have been at least 37 fatalities, with more than 6 million acres burned. This is an urgent moment, and it's a moment that is sort of taking everybody by surprise, of course, in the sense that the shocking scale of it is quite staggering. And of course, it's hugely stressful, there's massive loss, and there's danger for many, many people. It's profoundly important for our planet, and I think it's really essential that we think about this in terms of what may be causing it. It's such a vivid example of the effects of global warming and climate change that it is striking people's imagination and their awareness of the problem, I think, more than many other things have done in the past. So when it comes to the phenomenon of wildfires, the Earth Institute is world renowned for its scientific leadership and information and sources of advice, and it's in great measure because of my guest today. Bioclimatologist Park Williams is a research professor at the Lamont Doherty Earth Observatory at Columbia University, where his investigations straddle climatology and ecology. And he makes use of Lamont's world-class tree ring laboratory to provide a record of climate variability for the past 1,200 years. Williams' research on climate variability and climate change and how these processes have impacted the planet has helped us improve our understanding of the effects of anthropogenic climate change on forests, wildfires, and the western United States. So without further ado, I'm going to warmly welcome Park Williams.
Thanks very much. I'm going to share my screen. Alex, could you just give me a thumbs up if you see my slide?
That looks great. Fantastic.
Great. Thank you. Okay, then I will begin. Thanks to everybody for joining for this lecture. And it comes at an important and concerning time. The last few weeks have definitely been a valuable reminder to all of us that we ultimately live in nature, and that is exemplified in this satellite image capturing massive wildfires in the West and a hurricane hitting the southeastern United States at once. Because of the attention that wildfire has been getting around the globe, as well as the massive politicization of the fires and their explanations, I have decided that if I go back in time, I would change the title of this talk to be this: an evidence-based explanation for increasing Western U.S. wildfire activity. And so this talk is going to focus exclusively on Western United States wildfire. And I say evidence-based here, it sounds unnecessary to say that, but many of the explanations that we hear in the media and that we hear in politics don't actually refer to data. And everything I say today may not be correct, but there's data behind it, and I will be showing you data. If you didn't come here to look at graphs this afternoon, that's totally fine. I think that you can still take away the main messages, but I will be showing a lot of graphs because it's important to communicate that the ideas that I'll be sharing today are backed by data. Before starting, I'd like to thank a source of funding, a grant from the Ziegler Family Foundation. That grant is specifically funding the time that I've spent working on the project that I'll be showing today. And if you feel like the last few weeks have been extraordinary in terms of fire, then you would be correct. There are hundreds of large wildfires, or have been hundreds of large wildfires burning across the Western US. Many of them are still burning. And this really got going very suddenly in mid-August. Things seemed fairly quiet up until mid-August. And then in mid-August, a record-breaking heat event coincided with an extremely rare pulse of lightning that occurred over several days as Tropical Storm Fausto fell apart, and the humidity from that storm came up across California. When that humidity interacted or intersected with the record-breaking heat in California, then convective storms were triggered. These types of storms are extremely rare in coastal California. They're much more common in the eastern US, summertime afternoon thunderstorms or monsoon storms in the Southwest. This is the type of storm that was occurring in mid-August in California. And as a result, fires were ignited across the region. Those fires burnt for a couple of weeks, and then a second pulse of wildfires started largely over Labor Day weekend in early September of this year, once again coinciding with another record-breaking set of a record-breaking sequence of daily temperatures. The fire, many of these fires have gotten a lot of attention internationally, and a large reason for that is the incredible rates of spread. Anytime I look at fire spread rates, I'm shocked. Here we're looking at the Creek Fire that occurred, or that began in I believe early September in the Sierra Nevada. In the first 24 hours, it grew 36,000 acres. In today's talk, I'll be using the term acre a lot, but not many people actually have much of a good intuition for what an acre means. So when you hear an acre, think of football field. This fire is spreading at the rate of about 1 football field every 2.6 seconds during its first 24 hours. The North Complex Fire, further north, started, I believe, on that same day, or maybe actually a couple weeks earlier, but it really started moving very quickly again on September 8th. This fire, during a peak period of growth on September 8th, was growing by 2,000 acres per hour, which comes out about 1 football field per 2 seconds, which again to me is it's just shocking hearing these numbers. The fastest fire spread rate that I'm familiar with occurred in the 2018 Camp Fire, which consumed the town of Paradise, California, tragically. And in that fire's first 25 minutes of spread, it was consuming about 490 acres per minute, which comes out to more than 7 football fields per second. All of these wildfires occurred under very warm conditions. And because of these 2 heat waves in particular, the last month and a half or so have been by far and away record-breaking for this time of year across a lot of the West, including California. The time series I'm showing here is a record of average summer or average daily high temperatures between August 10th and September 18th each year since 1981. And what you can see is that in 2020, daytime temperatures were on average about 5 degrees Fahrenheit warmer than the average over the preceding 39 years. Weather stations, of course, have been around a lot longer than just 40 years, and so we can look at individual weather stations and see that in August, the temperature records are being set all over the place. Each time you see a red dot, That's a weather station location that experienced at least one new daily temperature record in August 2020. Death Valley actually recorded a verified temperature of 130 degrees Fahrenheit, which I believe makes that the warmest temperature ever recorded anywhere on Earth, or at least ever recorded and officially verified. And this officially, California, or Death Valley, never mind, I was going to make a joke. In September 2020, we've seen more record-breaking temperature conditions. I grew up in California's Central Valley, where it was commonly very warm in the summertime. The warmest days were between probably 108 and 110 degrees. To see temperatures like that, or even exceeding that on the coast of California, is really, really remarkable. California's heat wave this year in September was really quite different than anything that I have witnessed on the West Coast. And as we've seen record-breaking temperatures across the West, we've also seen record-breaking wildfire activity. Here we're seeing a record of annual burned area across the Western United States. It goes back to 1984. 1984 is the year when our satellite records of burned area begin. And this is really important. The satellite records are a source of precise burned area information. We extend that information up through present using government records of fire. And even though 2020 is not over, it looks like we're already just surpassing the previous modern record for annual wildfire area in the Western US. Before moving to the next slide, I'd just like to give a shout out to a PhD student in my lab, Caroline Zhuang, who worked with me over the last several months to develop this data set. This data set represents about 17,000 wildfires from the region, and took quite a bit of effort to pull together. Caroline's doing great work. While we're just starting to nose past the previous record burned area 2012 for the Western US, California has already far exceeded the previous record already by over a factor of 2. In both cases, for the Western US and for California, the area burned has increased by somewhere between 4 and 5 times over the last 35 years. And so a really important question to address before moving further is one that doesn't get addressed nearly enough. And that is this necessarily a bad thing? We've seen this giant explosion of wildfires in the last 35 years, but wildfires are inherently a natural process. They've been occurring on the continents for hundreds of millions of years, ever since plants first made their way onto the continents. They have been burning. Walk through essentially any old growth forest in the Western United States, and you will see ancient fire scars embedded into the tree trunks, like the one that we see here in a giant sequoia tree. And we can tell a lot about the history of fire activity by actually looking at tree rings. Here we're seeing scars from past fires that occurred back in the old medieval period in the 12 and 1300s. These scars have been burned the tree's trunk, and the timing of those fire events has actually been embedded within the sequence of annual growth rings, allowing us to know which years were the big fire years across Western North America for many hundreds more years than we've been keeping formal records. So fire is a natural part of the landscape, and it shouldn't be inherently alarming right off the bat to learn that there's been an uptick in fire. Upticks in fire would have occurred even without us, very likely. But it's also a matter of perspective whether it's a bad thing. We, for the last century, have controlled fire very successfully. As a result of our dominance over the fire regime, we've been able to begin living in highly flammable, densely vegetated areas. And so fires in the last couple of decades have been increasingly putting people in harm's way. Whether or not fire is a natural process or not, people are coming in increasing conflict with fire. And even people who don't live in these so-called wildland urban interfaces, right, where fires are burning, people are being exposed to the consequences of fire across not only the West, but actually across the entire country. In the West, though, large cities, Portland, Seattle, San Francisco, all experience air quality this during periods this summer that rivaled the worst air quality observed anywhere on the planet. And finally, even though wildfire is a natural process that's healthy for many ecosystems, there have been wildfires that have occurred in recent decades that scientists believe are exhibiting signs or exhibiting unnatural ecological consequences. This picture exemplifies this. This is a ponderosa pine forest. So I'll describe a little bit later. Ponderosa pine forest in the Southwest. Before the interference from European Americans, ponderosa pine forests were burning anywhere between every 2 and 12 years. And as a result of these frequent burns, the understory was constantly kept clear and forests were much less dense with trees. And so forest fires in ponderosa pine forests would be very large, but it wouldn't necessarily be all that intense. It was probably pretty rare to have an entire stand of ponderosa pine trees, the way that we're seeing here, killed by an individual fire. Instead, a constant barrage of smaller, lower frequency fires would have kept the understory clearer and kept fires from getting to be extraordinarily intense the way that this one is. And finally, you can infer something about the current population's view towards fire by looking at this graph. In red, we're looking at the same figure I was showing earlier. This is our record of annual burned area. And in green, we're looking at the amount of money the federal government spent trying to fight fires. This doesn't include the post-fire consequences of fires. It's just what we spent fighting the fire. And you can see that as fires have been growing over the last several decades, we've been trying harder and harder, pouring more and more resources into trying to fight fires. And as I'll argue in just a few minutes, our approach towards suppressing essentially every fire is unsustainable, and that's been known for decades. And yet we're in this lock where we continue to do it basically as hard as we can to this day. And so we likely have a number of possible explanations for why forest fire, or why fire in the Western United States has been increasing in the last several decades. And in the rest of this talk, we'll be exploring the reasons, or the possible reasons, and trying to give some explanations. And in looking for explanations, the logical place to look is here. There are really 4 things that are required for any wildfire to spread. One is we need to have an abundance of fuel, vegetation to burn. That fuel needs to be dried out by climatically arid conditions. And so aridity is an essential part of creating a large fire. And ignition is, of course, the first thing that you need immediately after fuel to start a fire. And then finally, most large wildfires coincide with large wind events, which allow the fires to spread. And so we'll first start by looking into fuels and the effect of fuels. Here I'm just showing 2 dramatically different landscapes in the Western US that illustrate 2 dramatically different fuel types. On the left is a forest. Within that forest, trees are very dense. And if a fire were to burn through that forest, the fire wouldn't be all that limited by fuel availability. There's a lot to burn, but the fire won't make it very far unless the environment is really dry. Whereas on the right, this environment is very likely always dry enough to burn, but there's not always enough fuel to burn. And so if we were to look for the perfect conditions for wildfire in the desert scene on the right, the first thing we need is moisture to grow a bunch of fuel. And then dry conditions might dry that fuel out to allow it to burn. So let's just take a simple view, breaking the Western United States into 2 different land cover types, forest versus non-forest, and see how wildfire trends have behaved over the last 35 years since our satellite record begins. And from these 2 plots, it's really clear that burned areas have increased both in forest and in non-forest. But this increase has been much larger in forests than in non-forests. And the takeaway here is that it's actually forest fire that is the main contributor to the Western United States increase in wildfire across over the last 35 years or so. But it's very important to take a long-term perspective on this. And that's what we do here. One of the neatest things that humans figured out how to do is to extract clues from past environments from the environment itself. One way we can do that is by digging into the mud buried at the bottoms of lakes. For thousands of years, lakes in the Western United States have been accumulating mud and other stuff that falls into the water. And some of that stuff includes charcoal from fires. And because all this stuff falls into the water in sequential chronological order, if we dig out a tube of mud at the bottom of the lake, then it's going to tell us information about wildfire variability over time. And that's what's shown in this graph. This graph is showing an average graph of charcoal abundance in Western United States lakes that covers the last 1,400 years. And what we can see are pretty big swings from decade to decade and century to century in wildfire activity across the Western US. The dotted line then is an estimate of how much wildfire we think should have occurred in any given decade or century based on drought information. That drought information comes from tree rings. And what we can see is that these two records go hand in hand. When it gets drier, we get more fire. When it gets wetter, we get less fire. And that occurred over the last 1,500 years until things became unhinged about 100 years ago. About 100 years ago, the data tell us that we should have actually seen more fire, but instead, fire was essentially eliminated from the landscape because of the introduction of aggressive wildfire suppression measures brought into the West from the East. Scientists refer to this process, this unhinging of the fire regime from the natural relationship with climate as the accumulation of fire deficit. And this picture nicely illustrates what I'm talking about with this fire deficit. We have a pair of pictures here of the Yosemite Valley, 100 years apart, or 112 or so years apart. And we can see a dramatic difference in forest cover. The difference is that after 100 years of successful fire suppression, the forest in Yosemite Valley is much denser than it would have been if fires were allowed to burn through here as frequently as they were before European American interference with fire suppression. This photograph is illustrative of many forests across the Western United States. Really any forest that prior to fire suppression was experiencing frequent fires would be susceptible to this fire deficit. The reason we call it a fire deficit is because now with more trees on the landscape, or as we've accumulated trees on the landscape, then we're increasing the probability very likely that a fire will eventually become so intense that we have large-scale tree mortality and rapid fire growth that escapes our ability to control. And the theory then, the point is that even without climate change, we would expect that our unsustainable approach toward fire suppression has been loading the dice for larger and larger fires. I don't know specifically when we would expect this to start having a major influence without climate change, but even without climate change, these dice would be loaded and we'd probably be seeing larger fires. However, this fire deficit narrative is, in my opinion, overly relied on to explain Western United States fire trends. It is not applicable everywhere. For example, there are some forests where we actually haven't been suppressing fires as intensively. For example, in national wilderness areas, we have not been suppressing fires nearly as aggressively. It is policy to allow lightning-started fires to play out as much as is possible. And when we look just in these national wilderness areas, we see large increases in wildfire as well. Also, this fire deficit narrative is really only applicable to forests that without fire suppression would have been experiencing a very high frequency of low intensity fires, keeping forest densities low. But in the wetter parts of the northern Rockies and the Pacific Northwest, it wasn't the norm to have fires burning through every 5 to 15 years or so, keeping forest densities low. Instead, forests could grow for a century or even a few centuries without seeing a fire. Forests would get very dense, and then during an unlucky drought year, they may burn in a large catastrophic stand replacing fire. That was the norm, and because that was the norm, our fire suppression strategy or policy probably has not led to an artificially high density of trees in all forests across the Western United States, but many of them it probably has. And so I'm trying to point out here what I believe is a false dichotomy that's been developing and popularized in the media and by politicians, and it really is not helpful in our, as we need to develop ways of coping with this clear conflict that we have between society in the West and fires that are burning. I showed some paleo information a minute ago, drawing on charcoal data from the bottoms of lakes, telling us that indeed, prior to European interference and fire suppression, it was the warm and dry periods that had very high rates of wildfire activity across Western North America. And so why would that not also be important today? And I'm going to show in the next sequence of slides that it very likely has been important in explaining the increase in wildfire activity. And so we're going to turn to the aridity part of the talk now. And the first variable we'll look at is a variable that I call the fuel dryness. And this is a calculation. We use climate model or climate data to make this calculation. And the calculation is an estimate of the moisture content of dead logs. Specifically, these are logs that are large enough where they respond to climate on the order of about 1,000 hours or so. And we can calculate the summer average fuel dryness anomaly, and that's what's plotted here over the last 40 years. And you can see that over the last 40 years, or I'm sorry, about 35 years, we've seen an increase in fuel dryness. And now I'm going to plot on top of that a record of our Western United States annual forest fire area. And you should be able to see a pretty good correspondence here. The years with very little forest fire are the years when conditions were cool and dry and cool and wet and fuels therefore had high moisture content. And the years with the highest burned areas were the years with warmer, drier conditions. Another way of displaying this relationship and investigating a little further is through a scatter plot. And in this scatter plot, each dot represents a year from 1984 through 2019. And this scatter plot, I think, really nicely illustrates this consistent relationship that we've seen over the last 35 years, where the cooler and wetter years have less forest fire area, and the warmer and drier years have more forest fire area. And this relationship alone explains about 75% of the year-to-year variability. But the other important thing here is that it's not just the year-to-year variability that fuel dryness seems to explain, it's the decade-to-decade variability as well, and that's important for interpreting trends. The different colors of these dots represent two different periods. The blue dots represent years in the 1900s, and the red dots represent years in the 2000s. And you can see they cluster fairly separately, where the 1900s tended to be cooler and wetter. The red dots, the 2000s, tended to be warmer and drier. And you can see that the difference in burned area between the 2000s and the final decades of the 1900s was about consistent with what you'd expect based on the relationship between fuel dryness and burned area that was already established in the 1900s. We see that this relationship strengthens even more if we look at another variable called the vapor pressure deficit. The vapor pressure deficit, many of you probably have not heard about or thought about much, but I hope you do after this talk. It is an extremely important variable, and it's not nearly as complicated as it might sound. It effectively represents the evaporative demand of the atmosphere. Technically, the vapor pressure deficit is the difference between the amount of water vapor that could possibly fit in the atmosphere, and that's dictated by temperature, and the amount of water vapor that's actually in the atmosphere, and that's humidity. And so as temperatures go up, the evaporative demand of the atmosphere goes up because the vapor pressure deficit goes up. There's effectively more space in the atmosphere available for the accumulation of water vapor molecules. And whether we're aware of it or not, we probably dictate some of our behaviors around this rule because we're all familiar probably with the fact that if we warm the air in our house up or dry the air in the house out, then house plants lose the moisture. We need to water the plants more regularly. Well, in nature, when we warm up the air, then plants lose moisture more easily, as does dead vegetation, and that makes it more flammable. When we look at this relationship, 79% of the variability in burned area may be explained by variability in the vapor pressure deficit. And again, we see that this relationship is not only consistent on the year-to-year basis, but it's also consistent on the decade-to-decade basis. And this plot has me convinced that we could not have seen as large of an increase in burned area as what we actually saw if it wasn't for the increase we observed in the last 35 years in the vapor pressure deficit. And I'll explain a little in a few more minutes why the logic behind believing that this trend that we've seen over the last 35 years is part of a global human-caused climate change trend. So wait a second, am I now saying that global warming is responsible for the increase in burned area and mismanagement of forests wasn't? No, it's not that simple. Here we're looking at this same scatter plot, but now broken out between non-forest and forest. And you see that when we go over to the non-forested landscapes, this relationship with vapor pressure deficit starts falling apart. It's still certainly there. The drier years tend to be the years with more burned area, but it's not as strong. And the interpretation here is because in these non-forest environments, we have a limitation of fuel in many of these places that might very well be warm and dry enough to support fire if there was enough fuel, but there may just not be enough fuel. The non-forest environments also tend to be environments with high population densities where people have more of an ability to muck around with the fire regime by setting fires and by very effectively putting out fires. And that segues nicely into the third branch of this fire triangle in the top left corner, ignitions. There's no doubt that ignitions from humans have completely transformed the Western United States fire regime over the last century or so. This map is showing the percent of wildfires that are due to humans as opposed to lightning. The red areas are areas where humans really dominate the amount of ignitions relative to lightning. In most of California, humans are supplying the vast majority of ignitions, although this is not always true, as we just learned in August with the very rare lightning storms in coastal California. And if we look at fires throughout the year, we see that humans have really lengthened the fire season. Humans are setting fires in the spring and in the fall when lightning is really rare, and humans contribute a giant rush of additional fires in the middle of summer associated with fireworks from the 4th of July. And human population in the Western United States has increased dramatically even in the last, or even during this study period of the last 30 to 40 years. Human populations increased by 36%. If each person brings with them an increased chance of an accidental spark and an accidental wildfire, then you can theorize that an increased human population may also be contributing to this increase in wildfire activity. But we actually don't see evidence for that. Here I'm plotting the annual number of wildfires. Now here I'm looking just at wildfires larger than 100 hectares or about 2 football fields. It's about 250 acres. So humans are setting a lot of smaller fires, but they're really good at putting out those smaller fires. But the fires that might escape or that escape initial suppression attempts, that's what's being represented here. And we're seeing that even though the population of the West has increased, we have not seen an increase in the frequency of the number of out of control wildfires in the Western U.S. And what this implies is that the increase in wildfire activity in the Western U.S. is not due to increase in fires. It's increase in the number of fires. It's due to the increase in the size of fires. And very interestingly, this data set here, it's not as long, but it's an awesome data set because it gives us information on the cause of individual fires. And here we see that actually, it's not even human-caused fires that are driving the increase in burned area. The increase in burned area is actually being dominated by fires caused by lightning. Lightning activity, I also don't believe has been increasing, or else we'd be seeing an increase in the number of fires. Instead, each lightning strike appears to be growing more potent in its ability to cause a fire to be large. And the reason for this, the reason why warming the reason why warming may be having dramatic influences on the potency of an individual spark and its ability to cause a large wildfire is because of what's illustrated here. It's that the relationship between dryness and the size of wildfires actually turns out to be exponential. This scatter plot I was showing you earlier is a little bit tricky because the vertical axis here is actually plotted on a log scale. You can see that these values are not increasing linearly. The reason it's plotted like this is to show this relationship seems to have been consistent over the years and decades in the past 35 years or so. But if we now plot all these points out on their native linear scale, we can see this relationship is actually exponential. And this is really important to understand, as is any exponential process. The spread of a virus, for example, tends to occur exponentially, which is what can allow a very small number of people with the virus to turn into a very large number of people very, very quickly. This same concept may be at play here. Over the last 35 years, temperatures have increased by somewhere between 2 and 3 degrees Fahrenheit. And I'm arguing that much of the increase in burned area that we've seen appears to be promoted by that 2 or 3 degree Fahrenheit warming. This nonlinear relationship indicates, however, that the next 2 to 3 degrees Fahrenheit warming would cause a substantial increase in the size of fires. This is so substantial. This is not realistic. This relationship cannot go on indefinitely into the future, into warmer and drier conditions, because we'd simply run out of forest to burn pretty quickly. And this is I show this in order to illustrate why, even though a increase in wildfire activity isn't on its own an alarming thing, why we should be thinking about what the future is going to look like now. Because if this relationship does hold, and if it turns out that the vapor pressure deficit really is a strong dictator of burned areas, then we should expect that even though we're seeing wildfire activity that we think of as being very extreme, there may still be a lot of room for more. And so finally, I'll wrap up by talking about human-caused climate change. Here we're looking at records of climate in the Western United States. The black record are our observations of temperature on the left and vapor pressure deficit on the right over the last century across the Western United States. And you can see that temperatures have increased and vapor pressure deficits have increased as well. That link is straightforward. Once again, when you warm air, then its thirst for moisture increases. Effectively, its sponginess increases. And that's indicated by an increase in the vapor pressure deficit. And then one of the other cool things that humans have figured out how to do is to simulate climate in computer models. And this is a hugely valuable tool because we can then use computer models to experiment with what would happen to climate if we were to do X, Y, or Z to it. And one of the experiments that has been run over and over again is what should Earth's climate do if we were to increase the concentration of greenhouse gases in its atmosphere? And the computer models say that it should warm. And when we ask the computer models, what if the greenhouse gas accumulation goes the way that it actually did over the last century, then the computer models say that the Western United States should have warmed by about 3 degrees Fahrenheit, which is really in line with what we observe. They also say that the vapor pressure deficit should have increased by 10 to 15% over the last century, and that's also in line with the trends that we observed. We can then use these computer models to experiment into the future, where we say, what if we continue burning greenhouse gases and we do so as fast as humanly possible? Or what if we take a different approach where the globe slows down its greenhouse gas emissions? And that's what's shown here. And what we're seeing is that if these computer models are anywhere in an accurate ballpark, we should expect warming to continue in the Western United States for decades to come. Here we're looking at two different greenhouse gas emission scenarios. One is this aggressive scenario where we're basically burning fossil fuels as fast as we can. Hopefully this is an unrealistically aggressive scenario. And the other is a more moderate scenario where the globe starts coming to agreements about how it is going to consume greenhouse gas emissions. When I'm referring to greenhouse gas emissions, I'm really referring mostly to carbon dioxide. This is the key greenhouse gas responsible for the current global warming trends according to computer models and theory. And we began measuring carbon dioxide in the atmosphere back in the 1950s. And since the 1950s, carbon dioxide in the atmosphere everywhere has been increasing steadily. And just a few years ago, we've surpassed 411 parts per million, very likely for the first time in at least 3 million years. Where is this carbon dioxide coming from, and why is it the byproduct of our energy? Well, the answer, turns out, is an ancient one. The energy that we're using today is actually ancient energy. Hundreds of millions of years ago, plants were growing just as they are today. They were growing using carbon dioxide out of the atmosphere for carbon and using sunlight for energy. Those plants and the organisms that were using those plants were then buried for hundreds of millions of years, turned into coal and oil, and we're now digging out that old carbon, putting the carbon into the atmosphere, and using the energy to fuel life as we know it today. This leads to a greenhouse effect, and the greenhouse effect works similarly to the process that we're familiar with from just getting into our car after it's been sitting in the sun. The atmosphere is kind of like the car windshield, where it turns out the atmosphere and the car windshield are both transparent to solar radiation, meaning that solar energy has no problem getting into the atmosphere or getting into the inner car environment. But then the atmosphere and the car windshield are both similar in the way that they're opaque to long wave radiation that the Earth and that the car seats and steering wheel and dashboard use to try and radiate energy back to outer space. Earth's strategy for cooling off or to getting rid of the energy it absorbs from the sun is to radiate long wave energy back to outer space. But the CO2 in the atmosphere effectively works as a blanket, making it more difficult for this energy to escape to outer space, and the Earth then heats up, and it has to heat up in order to finally be able to produce more energy to finally squeeze long wave radiation back to outer space. This concept has been known of for hundreds of years. It's been known for hundreds of years that the Earth must have a greenhouse effect because the Earth's atmosphere at the surface is warmer than it should be just based on distance from the sun alone. In the 1850s, it was then discovered that carbon dioxide is an important greenhouse gas done by really cool experiments by John Tyndall, where he would effectively heat up a tube and pump different gases into this tube and then measure to see how long it takes the tube to cool off. And he found that when carbon dioxide went into the tube, then it took longer for the tube to cool off because carbon dioxide was having a potent greenhouse effect. That brings me to the end of the talk, and I'll just summarize what I hope you can take away, and that is that we've been living in a fairly unsustainable way in a couple different ways globally and in the West. In the Western United States, man's dominance over the Western United States fire regime turns out was unsustainable. Not only did we eliminate lightning-induced wildfires from the West, but we also eliminated wildfires that had been used by Native American societies for thousands of years before European Americans arrived and began suppressing wildfires aggressively. It turns out this is unsustainable because every time you fight a fire successfully, you effectively kick the can down the road. You allow fuels to accumulate. That increases the chances that the next fire grows quickly and intensely enough to escape our control. It's also been unsustainable to emit CO2 into the atmosphere faster than it can be naturally removed from the atmosphere. That is causing a warming trend globally and increasing the evaporative demand of the atmosphere. These two processes, the local unsustainable fire suppression effect of developing a fire deficit in many Western US forests, and our global unsustainable trend toward increasing CO2 and the greenhouse effect in the atmosphere, I believe are multiplying each other. And we're now in quite a pickle. Now we have warming and drying causing fire to increase very likely exponentially. and especially in forests. And this effect is being magnified in areas where forests are artificially dense. The reason they're artificially dense is because we've been aggressively fighting fires for the last century. And because we were so good at that for so long, we have now taken up residence in many of the Western United States wildlands and densely vegetated areas we're now living in. So when a fire gets going, our health and our property are put at stake, and we then fight the fires, kicking the can down the road. This is a wicked problem. The physical science part of it is actually probably one of the simpler parts. It in itself is very complicated. What to do about this on the global scale and at the local scale is also very, very complex. And we need to be working as hard as we can on the scientific research side and to understand the socioeconomics that will be involved with finding solutions that are undoubtedly going to be very problematic and complicated. And all of this work to find solutions is being slowed down by distracting false dichotomization, where these days it seems only okay for somebody to think that our wildfire problem is only caused by forest management problems or only caused by climate change. And indeed, or in fact, there are several reasons for our wildfire problem now. And again, wildfire is not necessarily bad everywhere, but the way that we are interacting with it in the West is unsustainable and needs to be changed. Thank you very much.
Wow, thank you very much, Park. A big round of applause from all the people here. So Park, that was great. We're going to open up the discussion to the audience. We've got questions coming in, quite a lot of questions. They're being triaged for us so that we can actually pick out a few. But I just wanted to start off by saying thank you. And maybe while the questions are coming in, you know, one of the things we're always concerned about when we're talking about the climate change is that it's sort of gloom and doom and things are going to get worse, which they probably are. But what are the solutions going to be? Because you sort of started talking about solutions a little bit, but have you got some ideal of what a more sustainable relationship between humans and forests and wildfires might look like in the West?
I anticipate several questions that are along these lines, so I'm glad that you asked right away. And so I'd first like to say that my role as a physical scientist, my expertise really ends at the physical science part. I'm nowhere near the expert that others are in the wickedly complicated socioeconomics that go into finding solutions. And this is important to recognize because scientists in many ways serve as society's eyes. And I think society is most likely to trust me as a scientist if I don't go too far out on limbs beyond what my eyes are seeing and start speculating on things that I really speculating based on things that I haven't spent that much time thinking about.
Okay.
But I will. So broadly, it's so important, I think, that we as a society recognize that this increase in wildfire activity that we've seen over the last few decades, regardless of the fact that prior to European interference, there were even bigger fires. Regardless of that fact, the increase we've seen in the last several decades has been very much against our will. We've been spending as much money as it takes to try and put these fires out, and it's not working. And that means that we have lost control of a fire regime that we once thought we had control over. And recognizing that on a societal scale is very important, because if everybody recognizes that actually it is an inevitability that the next few decades we're probably actually going to see bigger fires than what we've already seen, then people will make different decisions about where to live, most likely. They'll also make different decisions about the risks they're willing to take with forest management. Our forest management problems aren't just because there's some forest manager in office somewhere that has no idea what the real world actually works like. The Forest Service and the folks trying to put out all of our fires are responding to a demand from society. Society wants these fires put out. Society also, turns out, doesn't really like controlled burns. Controlled burns emit pollution of the atmosphere and cause lung damage, just like wildfires. And so society doesn't like controlled burns either, and society really doesn't like rolling the dice with the idea of accidentally losing control of a prescribed burn. And so instead, our prescribed burning efforts are really limited right now. We do them on a very small scale, and we, whether we like it or not, are relying on massive mega fires to do the job for us of thinning the forest and getting us out of the fire deficit.
Losing control. Who would have ever thought of using that word, that term? Anyway, this has been the year of losing control. Anyway, let me just quickly open this up to the audience. Mark, there's quite a lot of questions coming in, so I'm going to ask you if you could give really succinct answers, if that's okay, because I want to try and get.
Unlike my first one, sure.
No, that's fine. So the first thing is, should the insurance? This is from Jim. Should the insurance industry discourage human settlement in fire zones?
Bielsa, I really don't know. I don't know much about insurance. I'm maybe happy to say. My understanding is that the insurance companies in the West reevaluate their insurance policies on fire every year. And I'm not going to say what I think insurers should do, but I will say what somebody living in the West should do. They should recognize that a property that insurers didn't even think twice about insuring decades ago, those insurance companies are very likely considering majorly raising the rates or even eliminating the insurance policies. And so if we're thinking about getting a new house in the West, this is something that should be on our minds.
Okay, I don't know how many people's houses just went down in value as a result of what you just said. Anyway, so is there another quick question about the fire? You've talked exclusively about the Western US, but you know, the stuff we've seen in Australia, which is pretty amazing, the stuff we've seen in Greece, of course, even Siberia. Are these the same kinds of things, or would you more or less expect the same parameters to be involved, or do we just not know? Is it we've got a huge, amazing tree rings record for the Western US, so we know a lot about the Western US. What's the state of play? Can we just say you can apply what you've done there to the rest of the world or not?
I think that it's not as simple as applying what we've learned in the Western US to the rest of the world, but we're not totally clueless here. Science coming out of Australia indicates that, well, first of all, this giant burst of wildfires that occurred in Australia also occurred under exceptional heat and drought. Heat and drought, all else equal, will promote fire. As long as you've got a spark and enough to burn, you're going to get fire. But around the globe, we see very, very complex interactions between fuels, climate, and fire. And so it is in the Western U.S. is actually pretty unique in that it is a very seasonal climate. The Western U.S. is reliably dry every summertime. There's not all that much rain to get in the way of dampening the effect of warming, whereas in even the Eastern U.S. we have rain year-round, and that very likely makes the ability of warming to promote fire much muted.
So I should have said that was Kathy who actually prompted that question, Australia. Another question, will climatically altered fire cycles promote the growth of new species of trees? Jim asks.
Definitely. Before human interference, fire is a major driver of succession and determining a sequence of succession of species after species. In the Southwest or in the Rockies, for example, commonly after large wildfires in conifer forests, the species that will take over is aspen. These very intense fires that we're seeing in the Southwest, which are larger and more intense, or I should say the area of very intense stand replacing fire seems to be growing beyond what the forests are really suited to, then we are very likely in the midst of a species transition, forest transition from being dominated by ponderosa pine to being dominated by more fast-growing, drought-resistant shrub and grass species, especially those species that can resprout after fire in order to colonize a burned area much more rapidly than a ponderosa pine could.
Okay. And then Kim asks, we have seen this year with the creek fire that a lot of the burn was dead trees, plagued by beetles caused by rising temperatures. Have you added this effect into your studies?
This effect is a fascinating one. Everything I showed today is admittedly pretty simple. I was very crudely separating simply between forest and non-forest. In a deeper study, we definitely need to look at a more granular scale. The research on the effect of bark beetle killed trees on fire is actually really fascinating. It makes logical sense that if you kill an entire swath of trees by bark beetles, then that wood is going to be drier and more flammable, and therefore increase the probability of large wildfire in that area in subsequent years. But when scientists have actually gone to the data to see if that actually bears out, then my read of the literature is that that effect actually doesn't seem to be visible. And over the last 40 years or so, at least, the areas that have experienced large bark beetle outbreaks don't seem to actually have burned the higher frequency than areas where trees didn't get killed by bark beetles. Scientists who look more deeply at this have shown that in the first couple of years after big bark beetle outbreak, then those forests are indeed more susceptible. They're more flammable. The needles are still on the trees. We call this, I believe, like the orange phase. But then as the dead trees age and the needles start falling to the forest floor, then the flammability of the forest changes, the way that wind can move through the forest changes. And then flammability of those dead standing snags actually seems to go down.
Okay, so we're going to go fast now, but I'm going to ask you at the end for one very quick take-home message for everybody that you'd like us to, the audience, to take away. But before we get there, you indicated, I was going to ask you this question myself. You indicated the 2020's lightning strikes was rare. This is from Robert. Is there a reason to associate the intensity of these strikes with climate change? So you say they're rare, but we've seen a lot of strange things happen in the last few years, meteorological effects, etc. And is it possible that actually these strange things are actually going to become more common?
The short answer is that a changing climate, of course, has some effect on every process within the climate system. However, lightning events in coastal California are so rare that it's really hard to get even a long-term perspective on what we would call normal. In the East, lightning is occurring all the time and it's much easier. Studies show that as the globe warms, we should increase the frequency of lightning in the East. But I truly don't know what the lightning experts are saying about the effect of climate change on lightning on the West Coast, similar to the event that we just saw last month.
Okay, one last question. What about selective cutting of mature trees to reduce fuel density, sequester carbon in new wooden buildings, and increase CO2 absorption from new fast-growing trees? This is from Judy.
I am definitely in favor of selective forest management through thinning of forests. We've got ourselves into this fire deficit. If we don't want mega fires to be the thing that sorts out the fire deficit, then we need to play a role, and thinning is part of that. However, at the scale of the giant Western US forest, it's not realistic to think that we can thin the entire forest the way that some politicians suggest. Instead, we're going to have to prioritize the places where we really don't want fires escaping our control. And so those are the areas in and around communities most likely. And as is suggested, the research indicates that carbon sequestration potential in our forests may actually go up as a result of thinning, which is a bit counterintuitive, but it reduces the probability of having giant stand replacing wildfires and therefore increases the lifetime of an individual carbon molecule on our landscape.
Okay, I would love to ask you a lot of other questions. There's tons of questions coming in. I really want to find out what your exponential curve really gets people nervous. And so I guess the question is, just before you finish, I ask you for your take-home message. What does that mean? And we've experienced exponential pandemics, but when you talk about an exponential curve for forest fires, are you suggesting that actually things are going to carry on getting out of control, or are they? Is it going to somehow stop, or do you not know?
Well, I think that this is part of a global story. We, with our carbon dioxide emissions, are performing a fascinating but terrifying experiment. The paleo records tell us that globally changes in carbon dioxide concentration have caused massive swings in global climate in the past. Swings so strong that 55 million years ago, crocodiles were able to live in the Arctic. Carbon dioxide can cause major shifts in the way that water, temperature, and forests are distributed across the continents. As these changes play out, one of the ways that the changes will be affected is through wildfire. Wildfire is the way, or one of the primary ways probably, that Western forests are going to respond to climate change. We don't have all of the answers, but it does seem the relationship between temperature and vapor pressure deficit and the relationship between vapor pressure deficit and fire is so strong in the West, it's really, really hard to find a way out of the reasoning that warming is going to cause an increase in forest fire and is responsible for a large portion of the increase that we've seen in recent decades, with mismanagement then multiplying that effect.
So that sounds like a good take-home message. Or did you want to add anything else as a final take-home message?
I'll just say that my opinion is that we should all stop politicizing this idea. We're not helping. When somebody gives a politicized opinion about fire in any direction, saying it's caused by climate change entirely, or caused by forest mismanagement entirely, please know that that is a politicized opinion, and please insert some intelligence into the conversation and say, well, you know, actually fire is affected by fuel availability and climate. Both of those things have been changing, and they're both very likely important here.
Okay, well, thank you very much. Thanks, Park Williams. Thanks all the people who've asked questions tonight. These Earth Institute series are very exciting. We're looking forward to sharing them with other people. There'll be a recording of this lecture available via email tomorrow. I just wanted to say that the Earth Institute depends on philanthropy. And so please bear us in mind if you're thinking about things you want to support in the future. We are concerned about how to sustain the planet and human beings, and how to build the world's future environmental leaders. Please join us on October 26th. We're going to have another Earth lecture then, and we'll be joined by two of the world's leading experts on sea level rise, among the most urgent consequences of climate change that we need to think about, that will threaten millions of people. Thank you very much, and good night.